Okay, so this is section 3.5, Math 146. We're going to continue basically 3.4. We're going to extend this to the other four trigonometric graphs that we didn't really talk about in 3.4. So 3.4 focused on sine and cosine. This one's going to focus on the other four, which is going to be your tangent, cotangent, secant, and cosecant graphs. Um, what I'm going to say is that most of the transformations that you used in 3.4 for sine and cosine is going to hold true for the transformations for all the other four. There is one subtle difference, and that comes in with the tangent and cotangent graphs. Other than that, most of it's exactly the same. Now, there are going to be a couple of things that are going to happen with all the rest of these graphs that we didn't see for sine and cosine, but other than that, the transformations are the same. So we're going to group this into our tangent and cotangent, and then we are going to do our secant and cosecant. So let's start off with tangent and cotangent. Tangent, I like to start off with because it is really the third of the three primary trig functions that we're used to dealing with. Usually it's sine, cosine, and tangent. So let's take a look at what a tangent graph looks like. So a tangent graph, and I'm just going to kind of sketch this so that you see what it looks like in general, is going to look something like this. And it's going to keep on going. Now, before I put any of the values down, that is one period of a tangent. That's what one period of a tangent graph looks like. And this would be tangent that has not been shifted. So we'll just say that this is y equals tangent of x. So that's a standard tangent graph. What tangent, cotangent, secant, and cosecant all have that sine and cosine didn't have are asymptotes. Okay, these are all going to have vertical asymptotes attached to them. And that's because if you remember, tangent is defined as the sine of x divided by the cosine of x. Well, because you can't divide by 0, any place that makes the cosine of x 0 is going to create a vertical tangent line. It's going to create an undefined value in tangent. Well, that's going to happen at all of the odd powers of pi halves. So right here, you would have a vertical tangent line, and that would be at pi halves. Okay, 0 is not an odd power of pi halves, but if you go this direction, that would be at negative pi halves. And then because these graphs do kind of go on forever, the next place that you would actually have a vertical tangent line would be someplace out here, which is where 3 pi halves would be. And what this graph does is it's going to do the same thing over and over and over again. It will repeat itself. So basically the graph of tangent would look like this here. And then it's going to keep on doing the same thing in all directions. And then technically it would go out here and do the same thing. It's going to repeat itself over and over and over again with having those vertical tangent lines at the odd powers of pi halves. And again, if you don't remember that, just know that it's sine over cosine. So it's wherever cosine is 0, which is all the odd powers of pi halves. So that's where you're going to have your vertical asymptotes. The cotangent graph is really going to just basically be a reflection of tangent. If you remember the cotangent graph, cotangent is cosine over sine. So the shifting is going to be off by about pi halves, just like it is for sine and cosine. So it's going to shift pi halves units because sine is going to be 0 at 0, pi, 2 pi, and so on. So all the whole values of pi. And the entire graph is going to reflect, instead of being an increasing function like you see here, cotangent will be a decreasing function. So let's take a look real quick at what that graph would look like. So a cotangent graph, y equals cotangent of x. And again, remember that cotangent is the same thing as cosine over sine. So wherever sine of x is going to be 0, you will have a vertical asymptote. Well, sine of x is 0 at 0, pi, 2 pi, and so on. And then in the opposite direction as well, negative pi, negative 2 pi, every whole value of pi. And again, cotangent is going to reflect from tangent. So your cotangent graph, instead of going up, will come down like this. And it will repeat over and over again, infinitely. Looks something like that. And of course, these places where it hits, where it hits the x-axis, those are your zeros of tangent. So tangent of 0 is 0. This is going to be right in the middle, in between pi halves and 3 pi halves, which is at pi. Tangent of pi is going to be 0. And if you think about it, again, that makes sense. You want a function or a fraction, excuse me, to be 0, it's where the numerator is 0. So every place that sine of x is 0 for tangent will give you a 0. All the whole values of pi. And then likewise down here, for cotangent, it's all the places that cosine would give you 0, which is all of the odd pi halves. So that would be at pi halves, 3 pi halves, going backwards. That right there, I kind of missed that one. It would be negative pi halves, negative 3 pi halves, and so on. So that's your basic graphs. Now, one thing you should notice from both of these, and this is what differs then from all the other 4, is that the period, or one full cycle, so you can see how that graph repeats itself over and over again, but one full cycle is actually only between here and here, which, if you think about it, only takes pi units, not 2 pi units like it did for sine and cosine. And as a matter of fact, cosecant and secant will also be 2 pi. The only ones that are different are tangent and cotangent. They both only take pi units to go through one full cycle, or one period. So when you are trying to find the period, and this will go for both of them, instead of doing 2 pi divided by omega, it is just pi divided by the omega. That's the only difference. All the other shifting is done exactly the same. The A out in front is going to give you the amplitude, which again has to be positive. If it's negative, it will flip it over, it will reflect it. Again, I used a C and a D. The C divided by omega will give you your phase shift left and right, and then that D will give you the vertical shift up and down. None of that stuff changes. All that's the same. The only thing that will change is that tangent and cotangent have to go through pi units in order to go through one full cycle. Of course, unless there is something out in front of that to alter it. But in a standard one, it's pi, which is why you do pi divided by omega. All right, so that's tangent and cotangent. Now let's look at the graphs of secant and cosecant. Oh, and by the way, you should be able to tell by looking at these cotangent and tangent graphs that you are going to have domain restrictions. There are definitely x values in both cases that are going to be restricted. Okay, and that's all going to be based upon the shifting and your period and all that kind of stuff. So you'll have to do a little bit of figuring out to figure that out, but it's going to be some combination. And in this case, and I'll show you how this is written, because this is not something that we deal with a lot when we deal with domain. What we do, because this is going to be a cyclical issue with domain, what you can see once again is that it is all the odd powers of pi halves. So you would say that in this case, x cannot be k times pi halves, or k pi halves, where k is an odd integer. Okay, it's a strange way of having to write your domain, but that's how you would write the domain. We'll do the same thing for cotangent in a second. The range here, this is domain, the range is all real numbers, because tangent and cotangent go on forever up and down. So the range, and if you've never seen this before, that's the shorthand for all real numbers. That's negative infinity to infinity. So cotangent, similar idea. X in this case cannot be any whole value of pi. So it's k times pi, where k is a whole number or integer. As a matter of fact, let's say integer, because that would include all the negative whole numbers. And then once again, your range, this is domain, your range is all real numbers. It goes on forever up and down. All right, so again, that's tangent, cotangent. Let's now take a look at secant and cosecant. And I find the easiest way to figure out what secant and cosecant look like by sketching their reciprocals first. So what do I mean by that? So let's deal with y equals, let's do cosecant x. If I was going to do y equals cosecant x, I know that the reciprocal of cosecant is sine. So I'm going to sketch, and I dot it because it's not really the graph that I'm looking for. I'm going to sketch the graph of sine. Well, remember that cosecant is the same thing as 1 over sine of x. But because 1 over sine of x is going to have issues wherever sine is 0, so basically everywhere that I just hit the x-axis, we're going to have vertical asymptotes. So we'll have one here, right on the y-axis, way out here, over here, and so on, all the places where sine would have hit 0. And of course, this goes on forever in both directions. And since this is a reciprocal, this is the way the graph looks. The cosecant graph will actually hit the maximums and minimums of sine and then extend in the opposite directions. They are reciprocals. So the only thing that should be exactly the same value is when sine is 1 or negative 1, because I don't care if you take 1 or negative 1 and flip it over, it's still 1 or negative 1. So the same values for cosecant and sine are going to be at 1 and negative 1 at all of these locations. And then, for example, let's just say that when sine is 1/2, so maybe right here, the sine value gives you 1/2. Well, the reciprocal of 1/2, of course, is 2, which is going to be up here. Sine is also going to be 1/2 over here. The reciprocal of that is 2. And then the further and further you go away, or the closer and closer you get to 0, the further and further this thing's going to go up. So basically, your cosecant graph is going to look something like this, where it's going to start to ride the asymptotes and go on forever. And then when it's under the x-axis, it's going to do the same thing, but in this direction. And it's going to continue on this pattern forever. All of the same shifting is going to occur. The period for these things is 2 pi, and the reason it's 2 pi is because you have to account for all the positive and all the negative values. So basically your period here goes from here out to here. Again, that's pi, that's 2 pi, 0, negative pi, negative 2 pi. So it takes 2 pi units to go through the entire cycle before it would start to repeat, because you got to have the upper and the lower part all accounted for. So that is a 2 pi period. which means that just like for sine and cosine, if you want to find any kind of a changed period or shifted period of some kind, it's 2 pi over omega. Same exact idea. All the rest of the shifting holds true. Amplitude is going to be the same. Vertical shifting going to be the same. Phase shifting going to be the same. All right, and let's take a look at the last one, which is going to be our secant graph. Oops, that's supposed to be black. Nope, still not black. Try again. There we go. And we know that y equals secant of x is the same thing as 1 over cosine of x. So let's sketch a cosine graph. The cosine graph, we know that the standard cosine graph starts at its maximum, goes down through the midline to the minimum, and then back up to the maximum. So it will start like this, the maximum, come down, go back up, and then that pattern goes on forever in both directions. And once again, everywhere that cosine in this case is going to be 0, you're going to have a vertical asymptote since we can't divide by 0. So secant will have a vertical asymptote there, 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 and there, and that's going to be at pi halves, 3 pi halves, negative pi halves, so all the odd pi halves, negative 3 pi halves, that's where you'll have your vertical asymptote. And then once again, the exact same thing is going to hold true. The only places these graphs are going to be identical is where it's at the max or the min, because it's a reciprocal, so you can flip over 1 or negative 1, and it won't change anything. All the rest of the values will go in the opposite directions or away from the x-axis. So right here in the middle, your graph is going to go through that point at 1 and then extend on, riding the asymptotes. Down here, same thing. Down here, same thing. And then obviously I didn't draw the graph long enough, but this piece would go up like that and would keep on going to the right. I just didn't draw it enough. That one's going to do that and then go to the left and so on. So just like cosecant, all the shifting, all the period, everything is the same. Once again, you have to get through a full positive and negative cycle. So if you think about it from negative pi halves out to 3 pi halves, that covers the positive and the negative portions. That's still a period of 2 pi. All of the shifting is the same. So that's probably about all I'm going to want to spend on these graphs. These are important, not nearly as important as sine and cosine. I would say you definitely want to know your tangent graph because I think the 3 main ones are the most important ones. And then cotangent is a reflection of tangent, just shifted by pi halves. Secant and cosecant, you could always figure out by sketching the sine or the cosine part first and then doing like we just did here. So I think that's about it for this section. That should finish up this unit as well, and you should have enough to complete the homework.